So I'm going to do record, then going to share screen. Okay, and yesterday I remember I started about the second learning algorithm. The first one is perceptron. We can see perceptron is the concept is easy to understand. Okay, the second one is adaptive linear neurons. Okay, and here it also involves convergence of learning. Okay, so this is Adaline. So the abbreviation is called Adaline. Okay, Adaline. And this one, perceptron, you remember yesterday we discussed if we want to do learning, we can directly also use the sklearn library, as if they have the linear model perceptron. But Adaline, in that library, we don't have. So, but we have our own code. Okay. So for the Adaline, yesterday I also mentioned it's based on gradient descent. Okay, this is kind of the foundation. Okay, for machine learning, and Adaline is batched gradient descent, and there are also a stochastic. Later on we will see. Okay. So that's the key concept, gradient descent. Just remember batch, what all of this means, okay? And Adaline, there is another difference between Adaline and perceptron, is Adaline also use cost function, okay, cost function. And the goal for Adaline is to minimize that. And the cost function is a continuous function. Okay, it's a continuous function. And like over here, it's explained, it's the foundation, lays the foundation for other advanced algorithm like logistics, support vector machine, regression. Okay. And here that's the key difference between Adaline and perceptron is perceptron rely on unit step function. That's for perceptron, okay, unit percept, unit step. And the Adaline, it uses linear activation function. And here we shows, okay. So W, we also already know its weight. This is vector format, that's why we have that T, okay. So this WT, so that means T in mass, you know, that's a transpose. Okay, so this is vector format, okay? And then generally when we write as this, is it in math, you learn that. Okay, so the activation function, is it over here, it's what? It's a linear function. So it's just a linear, so use the weight, is it times the features. Okay, so this is vector format, and basically it can be the matrix, is it matrix format? So we know that. Okay, and this is a decision function, is it? So its activation is a linear combination, okay, of weight multiply the features. Okay, so this is a concept, and here, then let's see. So the bottom graph shows the Adaline. Okay, so Adaline, we have net input. Is a net input is what? Is WIXI, is it? For all samples, for I from 1, is it? I from 0 to n. And the 0, 1 is for bias. When I is 0, so W0, you remember, is represents the bias, is it? And if you compare with perceptron, the perceptron to use what? So this is unit step function. The unit step function for the error calculation, is it updates for the weight updates, okay? And over here, we use activation function. what is that activation function? Basically, it's just sigma wixi, is it? And the linear combination. Okay, we use this as our activation function. And our weight updates, because that's our goal, is that we try to find minimum optimum weight. So weight update, it's not like a perceptron, is it? Perceptron, it use the difference between target value, is it? And this is predicted. So the difference between this times the feature, is it? And then we have the learning rate. Is it? To update our weight, is it? And then your weight updated as W plus delta W, is it? So this is the updating part, is it? And we have a number of each iteration, is it? And each iteration we do this kind of calculation, is it? And then you update the weight, and then your weight will approach to the optimal value gradually, is it? That's that part. And over here, if you take a look, is it didn't update user target and predicted values difference. It uses some, we call it activation function, is it? So how it does that? So over here, it's going to use a concept called gradient descent concept. Okay, so we will see that. Anyway, so this is visual view how the difference between Adaline and the perceptron. And then, so here we have the concept called cost function. Okay, so what is the cost function? So in Adaline, the cost function is defined as sum of squared error. Okay, so squared error, so here we have target, is it? So this is target. Basically, this is that activation function, is it? Function, is it? So the difference between this two, and you square it, and you sum over all samples. Over all samples. So this is called the cost function. Cost function. Is it? Then just think about, if we can minimize this, then the weight is going to be optimal. Is it? Because phi, this function, is it? It's regarding z, but z is what? Z is w, and it's the multiplication of w and x vector, is it? So this is regarding, and x is known in math, and this is unknown, is it? And we try to minimize this error, is it? How do we do it? So in calculus, you know the concept, is it? So if you can do the partial derivation regarding each weight and set it to 0, and purely from math, you can also find the weight, each corresponding weight, is it? The features weight. So that's a math solution, okay? But we will see in machine learning, we are not going to use that, because if you try to solve the equation, it involves inverse of big matrix. And that will cause a problem, okay? That can cause problem a lot of times. Anyway, so that's the difference here, okay? So here we have the concept of cost function, okay? And where this concept come from? So basically the concept is suppose we just have a single feature, okay, and then we have target value, is it? And so these are all samples, is it? These are all samples, is it? And here we use some linear prediction, is it? Linear. So this is predicted, is it? And of course you have the difference, is it? Regarding each sample, is it? You have the difference, is it? So basically over here, this is our phi. Okay, that line is a linear one, is it? So for each sample, we have the difference, is it? So here, of course, the question is, you see, you can draw any kind of linear line, is it? But which one will give the minimum of all of the arrows? Is it the sum of the squared arrow? Then visually we can see probably this one. Is it probably this one? The other may give bigger arrows. So this one then is the best choice. The best choice is what? You need to find the best weight, is it? So that's the goal of the gradient descent concept, okay? And here says the main advantage of this linear activation function is it is differentiable. Is it? Because it's y minus sigma, is it w j x j? Is it regarding all of the regarding all of the weights, is it? And so because this w, is it? It's unknown. This is known. Y is known, is it? So if it is known in math, we know it's kind of can be treated as constant. Is it constant? Some constant, is it? Some constant. And then only this is unknown. As if it's unknown, if you try to find the minimum value, you can do derivative, is it? So that's why I said, okay, if you put this, is it? Set it to 0, is it? Then you can find the solution. You can find the solution for the weight, is it? And then that weight is the best weight that will lead the minimum value, the minimum value of this expression, okay? And so here said the cost function, is it? The cost function in this case, you can see it's the square of w, so purely regarding mass, is it? It's quadratic, is it? So it is convex. So it looks something like this, is it? So it looks something like this. So this is J, is it? And this is W, is it? So it looks something like, so here is a cost, here is a weight, is it? So it looks something like this. So convex, is it? Where is the minimum? Here is the minimum. Is it the cost, the lowest cost? Is it the lowest cost like we just draw? Is it? So you can, so that's corresponding to this best fit line. Is it? Of the other cases, they go to somewhere else, the weight, okay, on this curve, okay, convex. So we said then it is a optimization algorithm in this case. So how do we find this point? Is that we use a gradient descent. Of course, you can also use math to solve the equation. Is that like we previous? But here we will use a method called gradient descent to find a way that will minimize the cost. Okay, so what that concept is, let's see. Okay, so over here, the idea is the gradient. Gradient. The gradient basically is what? It's just the derivative. of this JW, is it? Of this JW, is it take derivative regarding J, is it? And then you can reach the minimum point, is it? Can reach the, but here, how do we do that? Is we have initial weight. Initial weight. Here we didn't directly derive WJ, okay, from this. We didn't set it to 0. We didn't do that. So here we use another concept. We call it gradient descent. Gradient descent. Okay, because if you try to solve that equation, it involves the inverse of big matrix. And the inverse of the big matrix for huge data, if you have a lot of features, that's probably going to be impossible. Okay, so a lot of times, and it's not achievable. So here we find a way is we have some initial weight, is it? And we are trying to find to step by step getting close to the minimum point. We call it a global cost minimum point. So each time you take some step, take some small step to move toward that point. Is it? So how do we do the step? That's, so the step. So step, so that's what our learning rate defines. You remember we define the learning rate, eta. Is it? So this defined because in math, you know, is it? So if you know the derivative, is it derivative? And if you know this small step, then you can find the delta W, is it? So this is purely from math, is it? So we trying to use the learning rate, so which each is small step, and then we gradually getting close to the minimum. So this is a learning rate, how it comes. Okay, so basically it's for step. Then over here it also involves, so learning rate. So you may see, because if the step is too small, then it takes, so if it's too small, it takes a lot of step to getting close to the minimum, is it? But if a step is too big, suppose each time you take like this step, is it? Then maybe it can cause some problem. So if the step, I define the step as like this big, is it? So go to this is a single step. Then the next, this single, then you will find, is it? It's going to overshoot, is it? So if it's overshoot, it's just back and forth, but it's never going to reach or getting close to the minimum point, is it? So overshoot, is it? So the learning rate, pick the right learning rate is also important, is it? But if the step is too small, then it will take a lot of steps to converge, is it? So this is a concept of gradient descent. Okay, basically it's just some derivative is regarding the cost function, is it? And then you have the learning rate, is it? You can find each step, how much I'm going to move toward the optimal W, is it? That's the optimum point for the weight, is it? And over here on our graph, so each of this is our delta W, is it? Delta W at each time. each time we take, so for each iteration, is it? Each iteration we have that delta W. Is it then getting close to find the getting close to the optimal weight. Okay, so this is gradient descent. And then let's see the Adaline, is it? So the weight update, so this is vector format. Is it for each one? It should be right like this. This is for each feature. For each feature. Okay, for each feature. Okay, and this is a vector format. Okay, so and what is that delta W? Is it the weight change, weight updates? Is it? So we already see it's a derivative of cost function. Is it regarding W? Is it? So this is a cost function. Is it? Take a partial derivative, is it regarding the corresponding weight, and times what? Times the rate. And it takes the opposite direction, is it? And what is that derivative to the weight, is it? So regarding each individual one, that should be, so for each individual feature, is it, to the corresponding feature, is it? And if you take a partial derivative to each of the features weight, we will come up with this solution. Okay, come up with solution. So the derivative to the weight is going to be the target value, is it, minus the linear activation, is it? And the times the corresponding the features value, is it? So here J is for individual feature. Okay, feature, and the I. So here all of the I, the superscript I is for one sample. Okay, one sample. But over here, we can see we have sigma. Is it? So what this means? This is to sum over all samples. Okay, so that's why we call this batch gradient descent. Okay, it's batch. So batch is regarding all samples. Okay, later on we will also learn stochastic, the online, then it's different story. Okay, so that's the idea here. And then next, let's see, how do we derive that? Is it? So the derivations, weight update is, we already see it's the derivative of cost over the specific weight times the learning rate. The learning rate determines how big each time the step is it? And this derivative is this part. Okay, and once you know this delta W update, then of course you know the weight, is it, at that iteration, is that you can update it for the next iteration. Okay, then, so here it involves how do you find this solution, okay? So you can see machine learning involves heavy math, okay, heavy math. So the partial derivative to each specific weight of the cost function, is it, the result is this. How do we come up with this? So we know this is a cost function, is it? It's the sum of the square, error, is it, SSE? okay, some square arrow. And then for the derivative, we know that you can take the, you can move this inside. So that's how this part works. Is it move 1.5 out? Is it? And for this one, how do we derive? Because phi z is what? Is phi wixi. Is it phi wixi? And to take this derivative, is it? So it's something x squared. You take a derivative, is it? So it's 2x derivative, is it? So that's general. That's how you comes to this point, is it? And for this one, and over here, so here I should write a z, is it? Z. And then z is what? Z is w times x, is it? So that's when you take a derivative and you just get the negative w, negative xi. So that's how you come with this result, okay? So in math, you learn, in calculus too, I believe you learn this. Okay, so that's all of the concept regarding Adaline. And the next, let's move to the coding part. I need to bring that back. Is this Adaline? No, this is Adaline. Okay, let's see. So then let's take a look at the Adaline, the coding. So like I said, sklearn doesn't have this model. Okay, so here we define our own Adaline, okay, class. And as usual, it has a learning rate, eta, number of iteration, okay. And learning rate, be careful, it's between 0 and 1 and 1, okay. And then we have weight, okay. And we also define cost, okay, so over here. So a lot of similar as perceptron. And then we have the constructor, so nothing new here. And we have the fit. Fit is for learning. Okay, so over here it's Adaline learning. So X, we know it's the feature of the features, is it? And the Y, remember it's the target, okay, it's target. And the dimension over here, is it? And also be careful, Y it's regarding, it's what? It's n samples, is it? So Y, the dimension is n samples times 1, is it? And X is what? Is n samples times features, is n features. Okay, so that's the dimension, okay. And then let's scroll. So let's see how this time it works, okay. So this time, if you take a close look and compare with the previous one, we have the outer loop for iteration. For iteration, is it? And iteration is what? Regarding here. Oh. Here, so suppose here is your initial weight. Initial weight, is it? So you take step, 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 step. Okay, so each iteration is each step, okay. So first we get net input, is it net input? And once we have net input, over here we call that activation function. Is it? Basically it's the linear combination, is it, of the weight and so here it's basically the feature and the weight times together, linear combination, is it? And here we have the arrow, is it? We have the arrow. And how do we find the weight updates, is it? So the weight update based on the learning rate, is it? Learning rate. And what? So it is eta, is it? Times y minus what? Minus this phi z, is it? Phi z. And so this is, and regarding what? Regarding the X, is it regarding the features? So that's how over here it does the dot product. Dot product. Is it arrow is what? Arrow is this part, is it? And the X transpose. So this is X transpose in mass, is it? So this over here, this X is the matrix format, is it? So this X is this part, is it? So this is because this is the vector format, is it? So over here, it's going to find the corresponding weight updates, is it? And the same thing for the bias part, is it? And then we can also find the cost. So over here, the cost basically is what? This cost is at SSE. Is it a sum of square error? Okay. And then for each iteration, is it? Each iteration, we will have the cost be added to the sum of error be added to this error list, okay? So this is a fit. And if you compare this with the perceptron, you will find it only has a single loop, okay? Not like the other one has the outer loop regarding iteration and the inner loop regarding each individual sample, okay? So net input, nothing new, is it? And the activation function is just whatever the linear activation, okay? And the predict, is it? And then you can do the predict, is it? The predict, it depends on the net input, the activation function, is it? If it's greater or equal than 0, it's 1. Otherwise, -1. Okay, nothing new here. And then over here, it's the same thing. We just do here. So over here, same thing, is it? We read the CSV file from the IRIS data repository. So we get, and you remember totally we have 150 samples, is it? And here we get the tail, so the last 5, okay. So that's the concept here. And then next, let's see. So over here, the target is what? Is the last column. Okay, so last column defines what? Flower type, is it? And the features, we get what? We get sept length and petal length. So you specify the 2, is it? And here, when we do training, we use the first 100 samples, is it? So that's how we have this slicing, is it? Okay, and then next, let's see the remaining part. And we don't need to worry about plotting, okay? And so here we call that Adaline, is it? We just define. We have 10 iterations for both. We have 2 Adaline, AD1 and AD2, is it? And the first learning rate is 1%. The second is 0.1%, is it? And then we call the feet to do the training, is it? To do the training. Okay, that's this part. Okay, not a lot of new thing. And then over here, we do the plotting, okay? So what we plot is, the plotting is regarding iterations and the SSE, the sum of error, okay? The sum of error. So based on what we just described, you just think about this question. So so this is a number of iteration, is it? you increase the number of iteration. And here is the sum of the error, is it? So if our curves looks like this, or if the curve looks like this, so which one is better? Anyone knows the answer? Which one is better? You think like the SSE, the sum of square error, is it? The sum of square error is our cost function. Cost function. So ingredient descent. So the cost function versus the number of iterations. So if it grows, it's better, or if it is decrease, it's better. Anyone knows the answer? You just guess based on what we just learned? Can you kind of guess? Think about what is our goal here? Gradient descent, what is the gradient descent goal? Gradient descent goal is what? Is what? Is to minimize cost function. Is it? You remember that's the convex. Is it? That's a convex. So this is W, this is JW. Is it? So that's a convex. So it's to minimize. So minimize, then you think which one is better? Both curve. Okay, we have some chat. Let's see. Increase is better? No, not to increase. Is it? Our goal is to minimize. Is it? Let's see. One more. Yeah, the bottom. Is it? Yeah, the bottom graph is good. Is it? Because that's the goal. You want it with each iteration, if the cost becomes smaller and smaller, is it? And then it's good. Then how about this kind of case? Is it good? This kind of case? So it's sway back and forth, back and forth. Is that good? That's also not good, is it? Because only this case, this also tells us it converges. Converges. As you remember previously on that slide, we said converges. That means, oh, you are getting close to the minimum cost, okay? Okay, so here it shows us the first is with 0.01 learning rate. The second give a 0.0001 learning rate, is it? And we calculate it, and we also plot, and you can see clearly, is it the second one is better? Is it? This one is good. This is not good. Not good. That learning rate. Is it? So machine learning, later on we will see, also learn. There are a number of parameters you need to tune. So learning rate is one of the parameters. Okay, you tuning the parameter. Okay, and with the second one is good. Is it? The second one is good. Then we can use second one to predict. Is it predict? Okay, suppose we want to get 101 to 105. Is it? To predict what the type of flower is. Is it? So you get their X value, is it? And we also have the corresponding value. So that's the testing part. Is the testing part. And then you can also predict, is it? So we do have the result. Is it showing it's both are almost the same? Is it? So this means our model is doing good, is it? But if you take a look, if you use the first one, add 1, is it? Add 1, you will see the result. is it? So this is predicted. That's the target. Target is this is predicted. You will see the result doesn't match, is it? So it's really bad, is it? So here it once again proves our concept, is it? Okay, so over here, if you read the notes, okay, the read notes. So if the learning rate, is it learning rate, and if learning rate is too big, if it's too large, is it? And then it will kind of sway, is it? So it's like this. So it's kind of sway, is it? So that will not give a good result. That's not a good drawing. So it's should. So it's kind of. So that's not a good design. It's way too big. Is it? So learning rate, and if your learning rate is small, is it? Then it will getting close to that minimum point. Okay, so but of course, if the small, then it require larger number of iteration to converge to the global cost minimum. Okay, so that's the concept here, and then we can skip that part. Okay, skip that part. And then let's see, what do we have? Oh, okay, here. Let's see. And yesterday, I don't know if you still remember the standardization. Do you still remember what's the goal for standardization? For features? Who still remember? So what is the purpose? The purpose is to what? So who still remember that? And then you remember in sklearn, that belongs to the pre-processing. Is it? And who still remember that? Standardization. And how do we do standardization? Is what? X minus mu divided by theta. Is it? So the feature minus its mean. Is it? And this is standard deviation. Is it? Over standard deviation. This will bring what? Bring all features to the same what? Who still remember the same what? The word? The same scale. Is it? The same scale. So that it won't cause a huge problem, okay? So that's that the feature standardization, standardized feature. So here, we still use the original data, but we are going to do standardization. We're going to do standardization. And after we do standardization, we still use the Adaline. But this time, you see, the learning rate is not that very small one. It's a bigger one. Then we call fit. Call fit. And the call fit. And over here, if you take a look, we also plot what? We also plot the cost. Is it cost versus the iteration? Is it? And over here, if you take a look, did you see the result is pretty good? Is it? So this is number of iterations. Iterations, is it? This is what? This is that cost function. Is it cost function? So it decrease and converge. Is it? So you can see after we standardize feature, is it? Even though the eta previously we pick the bigger one, the result is bad, and this time the result is also good. Is it? So you can see in machine learning, there are a number of things we need to consider when we do the training. Is it not just a learning rate, and it also involves your feature needed to standardize. Okay. Okay, so that's the majority of the information, the major information. And basically, we finish this unit, okay?